Good morning, good afternoon, everyone. My name is Magdy, and today I'm presenting our research paper titled A Hybrid Oversampling Framework for Addressing Class Severe Imbalance in Network Intrusion Detection System using DSmote. This work was conducted alongside Dr. Wael from Elsersy. We are excited to share with you a novel approach that tackles one of the most persistent challenges in machine learning for cybersecurity, which is the class imbalance problem. The agenda. Let me quickly walk you through what we will be covering today. We will start by explaining what is an intrusion detection system, and then we will discuss the core problems that motivated this research. After that, we will review the existing solutions in the literature and their limitation. Then I will introduce our proposed method, the DSmote, and finally we will look at the results on two well-known benchmark dataset, which is the New South Wales dataset and the KDD Cup, before wrapping up with our conclusion. What is IDS? Let's begin with the basics. An intrusion detection system, or IDS, is a tool designed to monitor network or host activity in order to detect any malicious behavior. There are two main types of IDS. Signature-based IDS. This work by matching network traffic against a database of known attack signature. They are effective for known threats, but blind to the new ones. Second, we have anomaly-based IDS. This learn a model of a normal behavior and flag anything that deviates from it. They can catch novel attacks, but they came with their own challenges, which is exactly what we will talk about in the next slide. Second, what is the problem with IDS? We have class imbalance. In real network traffic, normal activity dominates. Attack samples are extremely rare. When you train a machine learning model on this kind of data, it learns to predict normal almost all the time, and technically achieve high accuracy, but completely misses the attacks. Second, we have the problem of high dimensional data. Network data is complex with many features. Traditional imbalance handling methods like simply duplicating minority samples fail to account for this complexity. They generate synthetic samples that don't reflect the true structure of the data. These two problems together are what we set out to address. As you can see in these charts, the New South Wales dataset is heavily skewed. The majority of the traffic records belong to the normal class, while the attack categories are drastically underrepresented. The KDD Cup dataset tell a similar story. While it's one of the most widely used IDS benchmark, it also suffers from extreme class imbalance. What are the existing solutions? Random oversampler. The simplest approach is random oversampler. It works by duplicating random samples from the minority class until the classes are more balanced. It's fast and simple, but there's a critical flaw. It doesn't introduce any new information. You are just repeating the same data points, which causes the model to overfit to those exact samples. It memorizes rather than learn. Smooth, the synthetic minority oversampling technique, improve on this by creating new synthetic sample. It does this by drawing a line between two minority class neighbors and placing a new sample somewhere along that line. This reduces overfitting compared to random duplication. However, Smooth has its own problems. The synthetic points can land in a sparse or empty regions of the feature space, creating noisy samples. Even worse, they can cross into majority class, leading to misclassification. Borderline Smooth is a smarter variant. Instead of generating samples everywhere, it focuses only on the borderline between classes, the hardest to classify samples. This sounds great in theory, but in high-dimensional data, class boundaries become poorly defined, and when the imbalance is severe, these borderline regions tend to be noisy, so the method generates unrealistic sample in exactly the areas where the data is most uncertain. Adaptive synthetic sampling. It generates more synthetic samples for minority points that are hardest to classify. The idea is clever, but it packs fire in high dimension, severely imbalanced data. Hard to learn points are often outliers, and generating more samples around outliers only amplifies the noise and lead to unstable minority class distribution. The gap we address, as you can see in a comparison table, all existing methods share a common weakness. They struggle with both high dimensional and severe imbalance simultaneously. Now, the DSmote. DSmote stands for Dynamic Smooth, and it's more than just another oversampling method. It's a hybrid framework. The key insight is, instead of blindly generating samples anywhere in the feature space, DSmote first understands the data through clustering and density estimation, and then control exactly where and how samples are generated. In short, DSmote understands the data structure through clustering and density analysis, reduce dimensionality before sampling to make the space more meaningful. It's not just oversampling, it's a full pre-processing pipeline. Now, let's have an overview of the DSmote pipeline. First, majority reduction. It reduced the dominance of the majority class. PCA. It reduced the dimensionality while preserving variance. Clustering. It divides minority samples into local groups. The density-aware mode generates synthetic samples only in the dense meaningful regions. Class weights. It further adjusts model sensitivity to the minority class. Let me walk you through each of these in detail. Step 1. Majority reduction. The first step is to reduce the size of majority class using a controlled ratio. By default, we keep 50% of the majority samples. Why do we do this? In extreme imbalance scenarios, the majority class is so dominant that even oversampling the minority class doesn't fully fix the bias. By reducing the majority, we create a more level playing field for the model without generating excessive or noisy synthetic minority samples. The model then has a better chance of actually learning the minority class patterns. Second, the PCA. Next, we apply principal component analysis to reduce the dimensionality of data, retaining 95 of the original variance. In high-dimensional spaces, the data is inherently sparse. Distance-based methods like DSmote become unreliable because points that appear close in high dimensions may not actually be semantically similar. PCA compresses the feature space to the most informative dimension, making distance measurement meaningful. It also removes noise and redundant feature, leading to more realistic synthetic samples. Third step is clustering. Now for each minority class, we apply k-mean clustering to divide the minority samples into 3 local groups. Instead of generating samples globally across the entire minority class, we generate them within each cluster. This preserves the local structure of the data. It prevents synthetic samples from being placed between two regions that are geographically close but semantically distinct, which is a major flaw in standard DSmote. Also, the in-clusters variable is a hyperparameter which you can adjust. Step 4. Density-aware sampling. This is the heart of DSmote. Within each cluster, we compute average distance between points using k-nearest neighbor. When generating a new synthetic sample through interpolation, we only accept it if its distance from the original point is within the average cluster density. This means we only place synthetic samples in dense, well-populated regions of the feature space, never in sparse or noisy areas. We also generate samples proportionally based on cluster size, so large clusters receive more synthetic points. This results for higher quality synthetic data and less noise. Step 5 is class weight. The final step is applying class weights to the classifier. Even after all the oversampling, we give the model an additional signal to pay more attention to the minority class during training. This further reduces bias towards the majority class. And now with the results on the New South Wales dataset. We evaluated DSmote across 6 different machine learning models: decision tree, random forest, XGBoost, assemble ANN, LSTMs, and 1D CNN. This ensures that our results are not model specific, and the DSmote benefits apply broadly across classical and deep learning approaches. Looking at the result of the New South Wales dataset, we can clearly see that DSmote consistently outperforms the baseline and other oversampling methods in terms of macro F1 score, balanced accuracy, and G-means, especially for the minority attack classes that were previously being ignored by the models. These charts further confirm performance improvement. The gains are practically notable for rare attacks categories, which is exactly what we set out to improve. Moving to the KDD Cup dataset, we applied the same 6 models. KDD is one of the most challenging benchmarks due to its extreme imbalance across attack subtypes. Again, DSmote demonstrates strong improvement across all models. The framework successfully lifts detection rates for minority attacks classes without sacrificing performance on the majority class. One honest trade-off to acknowledge: DSmote does introduce higher computational overhead compared to simpler models due to the PCA clustering and density estimation steps. However, since this is a pre-processing step done offline before training, the added time is acceptable. It's not intended for real-time on-the-fly deployment. Conclusion. To summarize, DSmote significantly enhanced performance on key metrics like micro F1, balanced accuracy, and G-mean, improving the detection of minority attack classes that simpler methods consistently fail to identify. Yes, DSmote comes with a higher computational cost compared to methods like random oversampling or standard DSmote, but for offline pre-processing pipeline, this trade-off is very much worthwhile. Overall, DSmote represents a powerful and reliable approach for improving intrusion detection on a highly imbalanced dataset. We believe this framework has a strong potential for real-world deployment in cybersecurity applications. Thank you.